Okay. Okay, we said that the same element has the same number of protons. But they can have differing numbers of neutrons. Differing number of neutrons. Okay. Therefore, the atomic weight of the atom of an element can vary depending on the number of neutrons it contains. The members of each element that have differing atomic weights are called isotopes. Okay. The atomic weight is protons plus neutrons. So obviously if they have a different number of neutrons, they're going to have a different weight. And this is called isotopes. When the same element has different atomic weights. Two elements can have the same mass number but never the same atomic number. We can figure out the number of neutrons in each case by subtracting the atomic number from the atomic weight. Two elements have the same number but never. So it's number of neutrons equals atomic mass minus the atomic number. So the atomic mass minus the atomic number, which is the number of protons. The isotopes are usually written in symbol form to make them easier to read. Oxygen, okay, oxygen isotope 16. I'm not going to make you put all these in your notes, but we are going to put one in here so you know how to read it. oxygen isotope 16 is written O16-8. O means oxygen. Sixteen is the isotope, or the number of neutrons. Sixteen is the atomic mass. 8 is the atomic number. Okay? So 16 is the atomic mass. Atomic mass. 8 is the atomic number, or the number of protons. Okay, so we subtract 16 minus 8 and we get 8. So the isotope is going to be 8. Okay. If you look at your periodic table, notice that each statement has its atomic weight listed. This number represents the average sum of protons plus neutrons of the element as it occurs naturally in our universe. Okay? So we said same elements have the same number of protons but differing number of neutrons. The atomic weight is the protons plus the neutrons. Isotopes are the neutron, which are the neutrons, is the atomic mass minus the atomic number. Oxygen isotope 16, this is how we write it. The O is oxygen. 16 is the atomic mass. 8 is this atomic number. We subtract it to get the isotope. Okay? Let's talk about beta particles. Beta particles are negative particles with a negative charge. Okay, so they're negative. They have a negative. I'm going to put a minus for negative charge. So they have a negative charge. They're found to be identical to the electrons that are in the outer paths of the atom. The only difference is that beta particles are high in energy and occur as a result of nuclear decay. Okay. They're high in energy. And they occur as a result of nuclear decay. So they're a result of nuclear decay. And we said they're in the outer paths of the atom. The outer path of the atom. These particles can travel at near the speed of light, 301,320 kilometers per second, or 186,000 miles per second. But because they have such a small mass, they cannot penetrate very far into any substance. For example, beta particles will only penetrate several millimeters into human tissue. Beta particles are symbolized by the Greek letter, kind of looks like a B. Okay, so beta particles are written like, sort of like this. Okay, that's the symbol for beta particles. The mass of an electron is negligible compared to the total mass of an atom. Therefore, the symbol for an electron or a beta particle often shows zero mass. Okay, let's talk about alpha particles. And that kind of looks like a cursive A, maybe. This is a symbol for alpha particles. Sometimes in nuclear decay, both protons and neutrons are emitted together in one particle. This particle is called an alpha particle and is made up of 2 protons and 2 neutrons. Okay. This is when nuclear decay puts protons and neutrons together to make one particle. Causes neutrons and protons to form one particle. Okay, and those are called alpha particles. And it says it's made up of 2 protons. So it has 2 protons and 2 neutrons. An alpha particle is just like a helium nucleus, but is emitted from the nucleus of some atom rather than being made from a helium atom. So it's just like helium. It's like a helium nucleus. And that symbol is 2He. But remember, it's emitted from the nucleus of an atom. Not from a helium atom. Not from a helium atom. The alpha particles, the Greek letter A, alpha particles, are very energetic, but they're relatively slow. Okay, it says they're energetic, but slow. They travel at speeds up to 21,000 kilometers per second or 13,000 miles per second. This speed covers a distance about half the circumference of the Earth in 1 second, but is only a fraction of the speed of light. Alpha particles are easily stopped and only penetrate the first few layers of skin. Since they're slow, they're easily stopped. Okay. We said that beta particles are high in energy, the result of nuclear decay, and they're on the outer path of the atom. Alpha particles, this is the symbol, is when nuclear decay causes neutrons and protons to form one particle. That particle is called an alpha particle. It consists of 2 protons and 2 neutrons. It's like helium. It's like a helium nucleus, but it's emitted from the nucleus of an atom, not from a helium atom. It's energetic but slow, and since it's slow, it's easily stopped. Okay? Now we're going to talk about gamma rays. Gamma rays have no charge. They're simply bundles of energy that are released from nuclei at the speed of light as the nucleus decays. Okay, so let's talk about gamma rays. And the symbol for gamma rays, I'm just going to put a Y. And it says they have no charge. And again, it's because the nucleus is decaying. They're formed when the nucleus decays. They're bundles of energy. They're released at the speed of light. From nuclei at speed of light as the nucleus decays. Because of their high energy, they're able to pass through or penetrate solids, including the ability to pass through a man. Several feet of concrete or lead are necessary to stop these rays. Okay. So these can pass through solids. So in order to stop them, it takes lead or concrete. I'm going to reword that. It says several feet of concrete or lead. Several feet of concrete or lead stops these rays, so stops them. Okay? Now let's discuss the positron. Positron. In 1932, okay, this is the symbol for a positron. It looks like it's 0 over plus 1 and then a lowercase e. Okay? This means positron. In 1832, Carl Anderson conducted a series of experiments with a device called a cloud chamber. This chamber contains a cloud of vapor similar to a cloud in the sky. Whenever a particle passes through the cloud chamber, it leaves a track in the cloud. By studying the track, the scientists can determine the particle's speed, mass, and charge. As a result of such a study, Anderson found evidence that a particle just like the electron existed. except this new particle had an opposite charge. Therefore, the new discovery was called a positron, because it was just like an electron, but a positive charge. Okay, so 1932, Carl Anderson and he used the cloud chamber Okay, we said that gamma rays, this is the symbol for gamma rays, a Y, it has no charge. Energy released from the nuclei at speed of light as the nucleus decays. It's able to pass through solids, even people. It takes several feet of concrete or lead to stop gamma rays. We're going to talk about a positron. This is the symbol for positron, 0 over plus 1, E. In 1932, Carl Anderson, he used a cloud chamber. And he said, with this cloud chamber, when particle passes through the cloud chamber, it leaves a track. Okay, so particle leaves a track. When it passes through the chamber, and by studying the track, Anderson found evidence that this existed. So through this he discovered a particle like an electron but had a positive charge. He discovered a particle like the electron with, I'm going to put a plus sign for positive, with a positive charge. And that's why he called it the positron. Okay? Look at the comic. Who are you doing your biography on? The girl says, Carl Anderson. The boy, what did he do? Girl, he discovered positrons. The boy, they have positive charges, right? The girl says, that's positively correct. Neutrino. Okay, the next particle we're going to talk about is the neutrino. And that's its symbol. Kind of like the same symbol for a verb. Since we live in an orderly universe, apparent contradictions to natural laws are reason enough to investigate. An example of such a contradiction is the disappearance of small amounts of energy during nuclear reactions. This apparent destruction of energy is contrary to the law of conservation of energy. To reconcile the apparent contradiction, scientists hypothesized the existence of a subatomic particle with certain characteristics and called it a neutrino. Okay. The law of conservation of energy states that you can't destroy energy. It just turns into an unusable form. And during nuclear reactions, it appears that some energy is lost. Okay, so the law of conservation of energy says energy isn't destroyed, it changes forms. So scientists hypothesized or guessed that a neutrino exists. And it says it has no charge, and very small mass. Evidence for the neutrino's existence is indirect, being proposed as a way to balance the natural laws governing the universe. Basically, whenever they had a nuclear reaction, it looked like amounts of energy were disappearing. So a neutrino is it's made in an effort to explain disappearing energy during nuclear reactions. Okay. So we said that Carl Anderson made a cloud chamber when a particle leaves the track. When it passes through the chamber. Discovering that track, they discovered a particle. Studying the track, they discovered a particle-like electron with a positive charge. Okay, the neutrino. This is the symbol for neutrino. It is the law of conservation of energy. Says energy isn't destroyed, it changes forms. A neutrino has no charge, and scientists believe it exists. They use it to explain disappearing energy during nuclear reactions. Neutrinos are very prevalent and more or less invisible. It's a very difficult particle to study because it's so elusive. It has no electrical charge. It affects matter only in a very weak manner. Trillions of neutrinos are zooming through you every second, yet you're not affected. As a matter of fact, about 1 neutrino per year will interact with you. With this level of interaction with nature, you can see the difficulty of studying it. Okay, let's talk about a meson. The other thing about neutrinos I'm going to put is that they're difficult to study. Difficult to study. Okay, we're going to talk about a meson. Nuclear particles. Okay, a meson, the symbol for meson looks kind of like the symbol for pi. Nuclear particles with a mass of about 1/8 the mass of protons are known as mesons. So they have a mass of 1/8 the mass of protons. They have a charge of positive, negative, or 0 and are very unstable. This is their charge. They can either have a positive, negative, or zero charge. The table of atomic particles summarizes 7 of the particles that make up the nucleus. Notice the difference in what the numbers signify. In this case, the bottom number indicates the charge of the particle. Okay, so mesons can be any charge. Let's talk about nuclear structure. Okay, we said that a neutrino is symbolized by the letters V. It is according to the law of conservation of energy, energy isn't destroyed, it changes forms. Neutrino has no charge. We use a neutrino to explain the disappearing energy during nuclear reactions. We're saying it doesn't disappear, it turns into a neutrino. Neutrinos are difficult to study. Okay? So let's talk about nuclear structure. The exact structure of the nucleus is unknown. It is known to be very complex. The puzzling fact is that the nucleus sticks together when we know that like charges repel. The charged particles in the nucleus would be like several dogs and cats stuffed into the same box, getting along perfectly. It doesn't fit the predicted pattern. So the exact structure of the nucleus is unknown. So the exact structure of nucleus is unknown. One theory suggests a model that arranges the protons and neutrons in a series of shells or energy levels like the electrons around the nucleus. The glue holding the nucleons together is the mesons, positrons, and neutrinos. The gamma rays are emitted when a proton or neutron drops to a lower energy level. Some nuclei are unstable. They have such a delicate balance of forces holding them together that the slightest disturbance will cause them to fly apart. This results in the radioactive decay we studied in section 2. So model. Protons and neutrons in a series of shells. Protons and neutrons are arranged in a series of shells or energy levels. Like the electrons around the nucleus. The glue holding the nucleus together. So it's saying that the mesons, positrons, and neutrinos are the glue that holds the nucleus together. It says gamma rays are emitted when a proton or neutron drops to a lower energy level. Gamma rays are emitted when a proton or neutron drops to a lower energy level, okay, some nuclei are unstable. Okay. This is one model. So we said the nuclear structure, we're going to talk about nuclear structure. The exact structure of the nucleus is unknown. One idea is the model. Protons and neutrons are arranged in series of shells. Mesons, positrons, and neutrinos are the glue which holds it together. Gamma rays are emitted when protons or neutron drops to lower energy level. Okay. Let's talk about stability. Stable nuclei are determined by the ratio of neutrons to protons. Okay, so it's determined by the ratio of neutrons to protons. Neutrons to protons. The greater the atomic number, the greater the number of neutrons necessary to keep the nucleus stable. The neutrons tend to act as a buffer among the protons, keeping them from repelling each other with such great force. If you look at that figure 9, it shows the ratio neutrons to protons necessary to ensure a stable isotope. Notice that as the atomic number increases, the number of neutrons must get larger to offset the increase in nuclear charge. Ratios that deviate very much from the curved line are unstable ratios and indicate the radioactive isotopes of that particular element. No completely stable nuclei are in elements 83 and above. All isotopes of elements beyond bismuth, 83, are unstable and radioactive. Okay. So basically, the greater number of neutrons, okay, the greater the atomic number, remember the atomic number is the protons, the greater the number of protons, the more neutrons it needs to keep it stable. That's what that's saying. Okay. And it said that no completely stable nuclei are in elements 83 or above. So there's no stable nuclei in elements 83 and above. All isotopes of elements beyond bismuth 83 are unstable and radioactive. You can conclude from this information that the interior structure of atoms is not fully understood. In fact, although several theories have been suggested, scientists do not understand what holds the nucleus together, in light of the fact that like positive charges of the protons should cause the nucleus to fly apart. There appears, therefore, to be an external unknown energy source which is available continuously to hold everything in the universe together. Because remember, of the scientific law, like charges repel. And it's saying that in a nucleus, if you have more than one proton, they should fight against each other, which should cause them to disintegrate. You know, it should cause an explosion. But that doesn't happen. So they know there's some kind of force that they have continually that holds them together. Somehow, electrons maintain their orbital energy continuously. Their negative charge should cause an attraction which would eventually cause an electron to plunge into the nucleus, because they fight against each other. Apparently, all electrons receive an energy input that allows them to behave as perpetual motion machines. This energy input is contrary to the established laws of science. Your previous studies have shown that perpetual motion is not possible in the current physical universe. Deductive reasoning, then, instructs us to look for a source of perpetual energy from outside the physical universe. Does the Bible give us insight into this mystery? The Apostle Paul states in Colossians 1:17 that Christ is the one who holds all things together. In Hebrews 1:3, we are told that Christ upholds all things by the word of his power. What can we conclude then? Science has shown us repeatedly that the entire universe is constantly moving toward a state of disorder. This has been established as the second law of thermodynamics. This condition of entropy, or disorder, started as a result of sin being introduced into the world by Adam. However, God in his mercy is apparently still sustaining the created order of original atomic structure by supplying the energy necessary to maintain this world. We owe not only our lives, but also the moment-by-moment sustenance of the physical universe to his active involvement. His grace allows us every reason to stand in awe, because of all the knowledge of modern technology cannot provide an adequate explanation for the origin or the continued existence of the cosmos. Okay, so we said that gamma rays are emitted when proton or neutron drops to a lower energy level. We talked about stability. Stability is determined by the ratio of neutrons to protons. The greater the atomic number, the greater the number of protons, the more neutrons are needed to keep it stable. No stable nuclei are in elements 83 and above. Like charges repel. And we just talked about the second law of thermodynamics. So I want to write that down. Second law of thermodynamics. The second law of thermodynamics states that the universe is moving towards a state of disorder. Is moving toward a state of disorder. And we said that God is the one that holds everything together. God holds all things together. Okay, I want you to go through and study your notes, study your lesson, and answer these questions.